Now the question is, can we measure the stress? No, we cannot directly measure the stress in a pipe or an object, but we can measure the strain, amount of deformation in a body. That's why we need to know the relationship between stress and strain to calculate the stresses in a pipe or a body. The second question is, why we have to calculate the stresses? We have to calculate the stresses so that we can predict when a pipe or an object is going to fail, when it is under stress or these stresses are within allowable limit of the code or not. If these stresses are within the allowable limits of the code or standard, then the pipe or an object will sustain these stresses for its entire life. So that's why we have to calculate the stresses. Let's discuss about the concept of strain and how to calculate strain. As you can see in the picture, when a uniaxial tensile force is applied on both ends of the rod length will change from L0 to delta L. In this case, the strain is the quantity of deformation occur in the body of the bar or a pipe, which is delta L. To calculate the strain, that is change in length divided by the original length L0 is called the strain, and it has no units. It is the ratio between the two lengths, and it is always expressed in percentage. Let's discuss about Poisson's ratio. It is a ratio between the lateral strain to linear strain, and this Poisson's ratio is always constant, and it is 0.3 for both carbon steel and SS in stainless steel material. For the both material, for carbon steel and SS, the Poisson's ratio is 0.3. Now the question is, which quantity first appear in a deformed body or an object? Either it's a stress or a strain. So the answer is, when external force applied to an object, it tries to deform the object, and when the object is deformed, means the strain occur in a body of an object, it will create stresses within a body of an object. As we explained earlier, we cannot measure stress directly, but we can measure the strain through strain gauges. Means amount of deformation in a body or an object we can measure easily. After measuring strain, we can calculate the stresses in a body or an object through the stress-strain relationship. That's why strain is independent quantity and stress is dependent on amount of deformation, mean the strain, and this is the reason in stress-strain diagram, strain is always plotted on x-axis and stress is plotted on y-axis due to the dependent quantity. So to calculate the stress from strain, we need to find out the relationship between these two quantities. So the relationship between stress and strain can be discussed in stress-strain diagram. Here, as you can see, this is the stress-strain diagram, and the strain is along the x-axis due to independent quantity, and stress is along the y-axis due to the dependent quantity. To understand the stress-strain relationship and the diagram, let's take an example of a specific material by performing a tensile test. The specimen in our case is a cylindrical rod, as you can see in this picture. It is fixed at one end, and a non-tensile load, which is 10 kg, is applied on the other end to measure the stress and strain in this test specimen. At the initial loading, there will be very minor deformation in the rod. The length of the rod will change from L to delta L, and area of the rod will start reducing. But this deformation will be very minor. And at this point, if we will remove the load, the rod will come back to its original length and shape. Let's increase the load from 10 kg to 100 kg. As we increase the load, the deformation in the rod will increase, and the length will be changed from L0 to delta L again, and area of the rod will reduce as well. Up till here, if we shall remove the load, the deformation will be reversed and rod will come back to its 100% original length and shape. This is called the elastic deformation, and in stress strain diagram it is denoted from point 0 to point A. Mean O to A, the straight relationship is called the elastic region or elastic deformation, and it is a linear relationship between stress and strain. We'll discuss further in next slides about this stress strain and the linear relationship about it. Let's increase the load from 100 kg to 1000 kg. If we will continue increasing the load, at this point the deformation will be permanent. Means even after removing the load, the rod will not come back to its 100% original position or a shape, but there will be some permanent deformation. Let's say 2% will be there. This 2% deformation is called the plastic deformation, and in stress strain diagram, from point A to point C is shown as a plastic region. And if we shall increase the load further, this plastic deformation will continue until the rod will break. This is called, the point C is called the breaking point. Let's see in detail the stress strain relationship with respect to this increase in load and with respect to the strain developed in the rod. The stress strain diagram has two major regions, elastic region and plastic region, as we discussed earlier. Elastic region, here the stresses and strains are linear. Whatever deformation occur within this region is fully reversible when the load is removed. This linear relationship is shown in stress strain diagram from point O to point A, and this linear relationship is defined by Hooke's law. What is the Hooke's law? That sigma is equal to E epsilon. E is the ratio between stress and strain and is called the Young's modulus. This region from O to A is also called the proportional limit or elastic limit of the material. The point A in this graph is called the proportional limit or elastic limit. Means after this point the yielding starts, and when the yielding will start in the material, from point B in this graph is called the upper yield point, and point C is called the lower yield point. Plastic deformation from point B till point E, this is called the plastic region. This plastic deformation or this plastic region consists of three subregions. One is called the plastic stage, second is called the strain hardening, and third one is called the necking. Let's discuss one by one. A plastic stage. In plastic stage, the strain increases at a faster rate than stress. This region consists of upper yield point B and lower yield point C. From point B till point D, this region is called strain hardening. And from point D till point E, this region is called necking. At point D, material achieves its ultimate tensile strength, and at point E, material breaks or fracture happened. But in true curve, fracture happened at point F. These things we'll discuss in detail in next slides. What is strain hardening? In this region, the permanent plastic deformation occurs in an object or a body, means after removal of the load or a force, material will not come back to its 100% original position or a shape. This plastic deformation is due to the strain hardening occur in the material. It means specimen still have some shape, but its dimensions will change, that is change in length or change in diameter or change in volume, etc. If same specimen again used for the test, it will show the same slope of stress strain curve, but it will not change the modulus of the material, means E will remain same. As a common understanding, after strain hardening, yield point of the material should decrease. However, the yield point of the material will increase due to strain hardening, as shown in the graph at point 3. When we unload the specimen after permanent deformation or a strain hardening, in our case at a point 3, that point now become new yield point of the same material. It means deformed specimen has more yield strength than undeformed specimen due to strain hardening. It means sigma deformed is greater than the yield strength or sigma yield undeformed material. This term is called the strain hardening. When yielding has ended, a further load can be applied to a specimen, resulting in a curve that rises continuously but become flat until it reaches the maximum stress called the ultimate tensile strength or ultimate tensile stress. This rise in curve is called strain hardening or work hardening. In engineering, we used word as work hardening. This strain hardening deform the crystal structure of the material and consequently material become weak, but experimentally proven that the deformed crystals are stronger due to strain hardening, as crystals have less space to move. Let's discuss about necking. After ultimate tensile strength of the material achieved, and if we will continue increasing the load or a force, then diameter of the specimen shall start reducing, and reduction in the area or the diameter of a specimen is called necking, as you can see in this picture. The length of the rod will change from L to delta L, and area of the rod will start reducing. When we increase the force, the area of the steel rod decreases, and this is called necking. At this point, rod will broken into two parts, and the area at this point shall be negligible or zero. It means stresses at that point will be ultimate. As a definition of necking, necking is sudden reduction in cross-section area of the specimen, and after that engineering stress decreases. As we know, sigma is equal to force over area. But in actual, even after ultimate tensile strength, the material gets stronger, and in true stress strain curve, the fracture point comes at a very high stress value as compared to fracture point in engineering stress strain curve. Hence, the end of the necking region comes at fracture point of a specimen.